Okay, hi everyone. Today we're going to start talking about the Milky Way galaxy, so our galaxy specifically. Before we get into it, I wanted to introduce some extra credit opportunities that I've come up with. So there's two different options or two different opportunities for you to get some extra credit. It's all posted on Canvas. So this completing these will add points to your lowest exam score. So it can bump up whatever your lowest exam score will be. You'll see there's an extra credit assignment page that's linked in the week 17 module because it'll be due in week 17. So if you scroll down in the modules, you'll see that extra credit assignment link, and it will give a little more detail. It shows the due date the Wednesday of week 17, so it's actually the class period before your final. And there's two options. So there's mapping rotation of the sky, and then there's also mapping phases of the moon. So the directions for these different opportunities, these activities, are linked there. So they're in the files of Canvas. So if you go to that extra credit assignment page in week 17, I have the instructions for both of these linked. So as you can imagine, if you're mapping rotation of the sky or phases of the moon, it requires an extended period of time. It's actually really cool and very fun to actually go outside and look at the sky, actually look up and draw what you see. They're pretty simple, but it does take some time. So if you're interested in doing any of these, make sure you start looking at them and working on them early, because it's going to take, you can't do it just in one day because it requires multiple observations of the sky during multiple nights. So you have to be prepared for the time that it will take. Don't try and start it in week 17. You won't have enough time to complete these. So if you're interested, make sure you're looking at them rather early or pretty soon so that you know you have time to finish them up. Today, we're going to talk about the Milky Way, our galaxy. We're going to talk about period and luminosity relationships. That's your first assignment, your lecture assignment. Also going to look at orbital motion within our galaxy and other galaxies, and rotational curves. So you're going to be able to read graphs of rotation curves. You'll be able to define the different key pieces of the galaxy and actually point to where they are, and also explain the spiral density wave theory. And then the last thing we're going to do is go over the two different hypotheses for how our galaxy actually formed. So that'll be what we do last. Galaxy. Our galaxy, it's seen from Earth as a really hazy band of light across the sky. So if you've been somewhere where you have a very good view of the sky, you'll see this hazy stripe, milky stripe, called the Milky Way. So both the ancient Greek and Roman people named the Milky Way something similar to Milky Way, either Milky Circle and Milky Road. So we took Milky Way from the Roman Milky Road. We now call this the Milky Way. So it was Galileo, if you remember, that determined the Milky Way is actually made up of millions of stars. And almost everything that we can see from Earth in the sky is part of the Milky Way. So almost everything we see from the surface of the Earth is part of the Milky Way. We can't see much beyond our own galaxy. So how do we know? How do we know anything about the Milky Way? A brother and sister team, Caroline and William Herschel, were actually the first to try and map the Milky Way. They wanted to map out the stars in the galaxy in 3 dimensions. So this was the first attempt to actually map out our galaxy in 3D. One assumption that they made was that they were able to see the edges of the Milky Way. So they thought that it might be plausible to actually map out all of the stars because they thought they were able to see all of the stars. They determined that the Milky Way is a disk shape. They also said that the sun is in the center and that there are some areas that they considered holes in the sky that have very few stars. So they did a very good job for what they had and were able to do for the start of studying our Milky Way, but we've made some corrections. They could not see the edges of the Milky Way. They assumed that they could see the whole thing, but definitely they could not. They were correct that the Milky Way is a disc shape, but they couldn't say much about the size. So it's true. And since then, we've determined that it is actually quite large, about 10 kiloparsecs in diameter and about 2 kiloparsecs thick. So it's much wider in diameter, of course, than it is in thickness. That's why we call it a disc shape. Their assumption or their discovery, quote, that the sun is near the center is incorrect. The sun is not in the center of our galaxy. And their holes in the sky, they were right that was something. They did correctly acknowledge that there were areas that they couldn't see, but what they didn't know is that it was the interstellar medium, so that ISM, that's actually blocking the view. So there are some areas that the ISM clouds the stars behind, so what they thought were holes in the sky, it's actually where ISM is present, but blocking the view of what's behind. So in 1912, Henrietta Leavitt, she was an astronomer that discovered variable stars. So variable stars are pulsating stars that pulse very regularly. So that's a regular timing pulsation. She found that the brightest stars have the longest pulse periods, and that all the stars in the same cloud, so the same cluster, are all the same distance from Earth. So we found that these variable stars pulse with a period between 1 and 60 days, so very different from pulsars, which we learned about previously. And when these variable stars exist, they are always within what we call this instability strip of the HR diagram. So this instability strip, this area of the HR diagram, whenever you have a star in this area, it can be a variable pulsating star. So we know from where this instability strip exists that these stars are going to be either giants or supergiants. So you can actually see how, let's say, a 9 solar mass star, so a star that's 9 times the size of the sun, will actually move as it ages in and out of that instability strip. So it can become a variable star and then stop being a variable star and then become a variable star again. So it's lower on the HR diagram, which means that the stars are smaller, are going to have quicker pulses, so faster pulses. Whereas the slower pulses that pulse with a longer time period in between are going to be higher on the HR diagram, or the larger stars. So you can see this here. A very large star might have a period of 50 days, where if you have a smaller star, still within that instability strip, so it's still a giant, just not quite a supergiant like this one, the pulse period might be only 3 days. So why do these variable stars pulse? This instability strip is sort of like a Goldilocks zone. So this is where the stars are not too hot and they're not too cold, and they can actually become unstable. So what happens is a layer of partially ionized helium in the atmosphere of the star will actually start to absorb and release energy. So that is the pulsing that we see, is the absorption and then release of photons from this layer of the star's atmosphere. If the star's too hot, the layer will be actually too high. If the star's too cool, then the layer will be too low, and we won't actually see the release and absorption of energy. So the star has to be sort of in this instability strip in order for it to be unstable and react with the helium. So it will absorb helium and then release helium. We know that when it is when that excited electron drops back down. so the release, we see a photon, or a photon is emitted, I should say. So we would see that pulsing light. So once the stars move out of the instability strip, the pulsing stops. So we can look at the period and luminosity relationship. So for variable stars, the absolute magnitude, or the also luminosity, is comparable to the period of the pulsation. So very bright stars with high absolute magnitude, which means they're very large, are going to have a larger period. So more of a pulsation period of 30 to 100 days, whereas very small or very dim stars are going to have a much quicker period with, say, less than a day between each pulse. So you can use the pulsation and the brightness to determine much more about these stars. So if you want to go in and do the first assignment, it's about graphs such as this. Just reading the period and luminosity relationship, understanding that relationship between different stars. If you want to go in and do that assignment now, that would be a good time. This is when I would have had you do it in class. If you want to wait till the end and do it all at the end, that's okay too. We're going to get into our galaxy itself. So the size of our galaxy we've been able to determine actually using that period and luminosity relationship. So that period and luminosity relationship allows us to calculate the distance to a star cluster that has variable stars, because we can calculate the distance to those variable stars using the apparent magnitude and the period of pulsation. So the apparent magnitude and the period we can use to find the absolute magnitude, and then knowing the absolute magnitude and the apparent magnitude, we can calculate the distance, which we've done before. A couple weeks ago, we used the apparent magnitude and the absolute magnitude to determine the distance to that object. So is it closer? Is it further than that 10 parsecs? So astronomers were able to determine that the center of our galaxy is actually not near our sun, and it's actually in the direction of Sagittarius. So we say the center of our galaxy is pointed towards Sagittarius. Our sun is actually not near the center at all. So if we look at a galaxy here, specifically our galaxy, there's a couple different components that I'm going to define and explain. The first being the disk. So the disk of our galaxy contains almost all of the gas and the dust in the stars, and almost all of star formation occurs in the disk of our galaxy. So the disk being this view, this top view of the galaxy, we would say is face on. So this is the center. Here we're seeing our disk. It's sort of like we're looking from above. This view here is edge on, so it's sort of if we were standing here, maybe on this word central budge, looking at our galaxy, so we're seeing the edge. So this flat area is the disk, which when we look from the top is this big disk. So the disk, if you remember, is very wide but not at all thick. That's why we call it a disk shape. It's the shape of like a CD. I hope that didn't just age myself too much. So this is what's happening if you're looking sort of at the top of the CD versus at the edge of the CD. You see the really thin edge of the disk. So most of the stars within this disk are low to middle main sequence stars, but most of the light actually comes from very, very few very bright stars. So there's a few stars that are very, very, very bright, and that is where most of the light actually comes from. So this disk of our galaxy is where most of the material of our galaxy actually exists. The next piece is the halo. So the halo being the spherical component of our galaxy. So the disk is it's three-dimensional, but you can think of it as something flat, something two-dimensional. The halo is the three-dimensional sphere all the way around. So it's a spherical cloud of some stars and star clusters, but there's very little gas and dust. There's really not much material, and there's no star formation in the halo. All the star formation of the galaxy occurs in the disk. The stars out here are very low main sequence stars. They're old and they're cool. They're often white dwarfs or red giants. And then we have what we call the central bulge. So the central bulge being truly the center part. So this center part here, it's white on the top here that I'm showing with the highlighter pen. It's billions of stars that are sort of flattened into a circular cloud. So it's in the center of the disk. There's here many stars, but not much gas and dust. So again, there isn't much star formation occurring in the central bulge. All the star formation is somewhere in the disk. So it's the halo, the large halo, and then the central bulge that are considered to be what we call the spherical components of our galaxy. So the galaxy is a sphere, even though really it looks like it's a disk because of our halo. So there's the halo and then the central bulge that are the spherical components. So when we think about our galaxy and the shape of our galaxy, we can think about the different orbits of the things within our galaxy. So stars that are within the disk are following circular orbits, but they are along the plane of the galaxy. So they circle around the disk. It's sort of like running around a track, if the galaxy was a track. Whereas halo stars and star clusters, they actually follow orbits that are tipped. So they're not running around the track. Their orbits are tipped at some angle. As you can see here, this orbit, the blue is where it is above the galactic plane, and then the dashed line is showing where it would dip below or, beneath the ground if this was the track. So they're not perfect ellipses, the halo stars, because the gravitational force or the pull of the bulge in the center actually warps and curves the orbits of these halo stars and star clusters that follow these tipped orbits. So there's two different types of orbits. Either you're in the disk and you are running around that track of that disk, or you are in the halo, that spherical component, and your orbit is going to be tipped in or out of that galactic plane. So the rotation of our galaxy is really the rotation of everything in the galaxy. So everything is rotating both together and separately. So each star is rotating around the galactic center. Here's our sun, for example, but at different rates. So we call this differential rotation. The distance from the center of the galaxy determines the revolutionary period, or like your year, sort of, how long it takes to circulate around the galactic center. So stars that are close to the galactic center have a shorter time period to rotate. Stars on the outside, it takes even longer to rotate around because they're further away. Their circumference is larger. So stars that maybe start close together are not going to end. They're not going to stay together for their whole lifetime as they rotate around in our galaxy. So this is differential rotation. So the different rates of rotation as you move from the galactic center outward. So if we look at curves of rotation, we can look at the distance from the galactic center here on the x-axis. So this is distance. If this is the galactic center, here we're 2 kiloparsecs away. Here we're 14 kiloparsecs away. So here we're very far. And then the orbital velocity. So what we call Keplerian motion is the perfect idealized what we think would happen, in that the fastest speeds are towards the center of the galaxy, and then the orbital velocity would decrease as we move away from the center. So as we move away from the center of the galaxy, the speed decreases. This is what we see for our solar system with the sun and the planets. However, for our galaxy, it's not quite the case. So our galaxy here is shown in the red line. So we actually notice that the outer disk, way over here, very far from the galactic center, is pretty constant, and actually there's this increase in speed here. So what this is saying is that the larger orbits, so the orbits that are very far from the galactic center, actually have a lot of mass. So there's a lot of mass held in these outer orbits that are further than even the sun's orbit in this figure. So there's a lot of mass in the outer reaches of our galaxy's orbit that makes this not fit the perfect curve like we might assume. So that extra mass is actually all within what we call the extended halo. The galactic corona is another way to call it, or what we call the spiral arms of the galaxy. So this extra mass in that extended halo, it actually reaches 10 times further than the edge of the visible disk. So 10 times further than the edge of what we actually see as the disk of our galaxy. And it's assumed that this extra mass is actually made up of more than 1 trillion solar masses. So the amount of mass that would be in about 1 trillion suns. So most is invisible, meaning that it doesn't emit or absorb light. So it would be considered dark matter, something that does not emit or absorb light. So again, that's why we do not see it. Some of the mass might be very low luminosity stars to the point where we still don't see them. But for most of this extra mass in this extended halo, way out past the edge of the visible part of the solar system, the galaxy, it's going to be invisible to us. We won't actually be able to see it. So when we think about the spiral arms of the Milky Way specifically, we're talking about these thick spiral arms. Well, they appear to be thick spiral arms that spiral outwards away from the center of the galaxy. So they're made of mostly clouds of dust and gas, hot, very young, and often blue stars. So there's a lot of star formation going on in these spiral arms. So some questions you might have is, how do we know? So isn't there ISM blocking us from measuring this, from seeing this, the same way that that brother and sister team found those holes in the sky? True, I'll get to it. And then also, how do these spiral arms exist, and how are they not destroyed by the differential rotation of our galaxy? So it's not that everything is going to spin at the same rate. You'd think that these spiral arms would be destroyed as the rate of rotation changes moving outwards. So let's explain both of those. So the spiral arms are mapped in a couple of different ways. So we use what we call spiral tracers. So spiral tracers are things that we can use to actually map out these spiral arms. So spiral tracers here. Some of them are groups of O and B stars, so very bright O and B stars that lie along those spiral arms. Groups of these stars are rather easy to detect. Also young star clusters, because we know that a lot of star formation occurs in these spiral arms. We would be looking for clusters of young stars. Emission nebula, some variable stars as well, and clouds of hydrogen that's been ionized by these very hot stars nearby. So we'd expect if there's a lot of star formation, there's a lot of young stars, there's a lot of very bright stars, we're going to have a lot of ionization of the hydrogen by all of those stars nearby. We also know that almost everything within these spiral arms is going to be pretty young because the objects have not had the time to move much from where they were formed. And most things are formed inside the spiral arms. So they haven't really left where they were formed. Otherwise, they would be older. So we know to expect young objects within the spiral arms. Other galaxies also have spiral arms. It's not just ours. Generally, when we're looking for the spiral arms, we're looking at really hot blue stars and other tracers, like I just talked about. And we know that other galaxies, it's true as well, that the spiral tracers are always pretty young. So you know when we're looking at spiral arms, we're looking at young areas of the galaxy where there is a lot of star formation occurring. So we can actually map spiral arms. The ISM does block in the visual a lot of the spiral arm. So we can't actually see these things in the visual. However, the workaround to still be able to map where these spiral arms are in space is using radio astronomy. So using radio waves, using spectral lines, of course we're coming back to spectral lines. So spectral line emission from carbon monoxide actually helps us determine where there are molecular clouds. So large areas of molecular clouds, you're going to have carbon monoxide, you're going to have emission there, and we're actually able to determine where these giant molecular clouds are located. And we know that these are areas of active star formation. If we have large molecular clouds, there's active star formation, so we can assume the active star formation occurring in the molecular clouds are on our spiral bands. So when we map out like this here, the locations of these molecular clouds, we actually see that they form bands. So we can map in three-dimensional space, which is a little tricky to look at. We can map where these molecular clouds are, and we can see that they form these spiral bands just as we would expect. So mapping, I'm not going to get too much into how we actually go about the mapping and the determining where the molecular clouds are, but there is we use radio astronomy and also Doppler shifts. So using the Doppler shift to see how things are moving relative to Earth, are they moving towards us or away from us, helps us determine where these clouds are and also how they are rotating. So it's a very cool workaround for this ISM dust in the way. The shape of our galaxies, so we don't have a picture like this. This is an artist's impression from our textbook, but using what we know about other galaxies and compared to ours, we can actually determine the shape. So our galaxy is a spiral galaxy, makes a spiral, but it's not a perfect spiral. There's some irregularities. So you'd expect a perfect spiral to have 1 and 2 here bands, but we have all these other smaller sort of side bands that are still important, but makes us not a perfect spiral. These extra sort of detached segments, we consider them spurs. So we call them spurs, or you might hear them called branches or secondary branches. That is an area similar to the spiral band that is not the main spiral band. So we actually have learned that this central bulge of our galaxy is not a sphere as it was first assumed. It's really more of an elongated bar, so sort of a rounded, elongated bar instead of being a perfect sphere in the center. So using observations of our own galaxy and then comparing those to other galaxies that we can see, we've been able to determine what our galaxy would look like. So this would be the face on, so sort of looking top down at our galaxy. So when we're thinking about spiral arms, we think about the spiral density wave theory. So spiral arms, they are not connected. It's not physically connected at all, because if they were, they would be destroyed by that differential rotation that we talked about. However, they aren't dynamically stable in that the spiral arms actually retain their shape and their appearance, even if the contents are changing all the time. So the textbook had a really good analogy for this. It's like a traffic jam behind a very slow truck. So even if you are stuck behind the truck and then you merge around the truck and then are able to speed up and keep going, there's still a traffic jam behind the truck. So behind that very slow truck, there's still going to be a traffic jam. So that's similar to the way that the spiral arms work, in that it's not the same material all the time, but there is always a large amount of material in these spiral arms. So the spiral density wave theory says that these dynamically stable regions, they are regions of compression that move really slowly around the galaxy. So gas clouds can move into and out of the spiral arms. So they sort of bump into the spiral arms. And if you remember when we talked about star formation, that's one of the ways to trigger the collapse of the ISM or of that gas cloud and actually form new stars. So this is one of the ways that this happens. It also keeps the spiral arms in place and in shape. Is that we have, let's see, this is a little time series of images from the textbook. So here we have our gas cloud. It's going to bump into the spiral arm. It's going to condense. It's going to trigger formation of new stars. So now we have the formation of new stars right on our spiral band. Our spiral arm. And then eventually this cloud and these stars are going to move out of that spiral arm as they age. So again, like I said, everything in the spiral arm is going to be relatively new because of this. So the time that they spend in that spiral arm is going to be while these stars are very, very young. Before they can actually leave, or before they end up moving on from the spiral arm, they will have aged quite a bit. And then they will continue their own motion around the galaxy. So get back to their previous motion around the galaxy. So there's a couple of problems with this theory in that it makes sense, but how does the spiral actually begin? So how did it start? And then also, how is it really sustained? So using models of the galaxy, we know that these bands should naturally collapse over time. They shouldn't be sustained. The spiral waves shouldn't exist forever. They should actually collapse. So the two different ideas in how does this occur for so long is that, one, maybe it's the gravitational effect of that central bulge. So that central bulge, remember, it's the bar shape in the center of our galaxy. Maybe that, the gravitational pull of that and the fact that it's not a sphere could actually perturb the galaxy enough to keep the spiral bands in place. Or two, is that the galaxy might encounter other galaxies nearby that could stimulate that spiral, that could cause that spiraling. So it's really not certain, because some galaxies don't have a central bar or don't have a central bulge that we know of in a way that it's not visible, but they still have spiral arms. So spiral wave theory makes sense, and it is what we go with, but we don't know everything about it. It doesn't answer all of the questions. With, a lot of aspects of astronomy, that's how it goes. Galaxies, we say they can vary between grand design and flocculent. So grand design means that a galaxy has two main arms. So I'm tracing them here. So there's one main arm, and then here's the second one. So there's two main, very, very clear spiral arms. Or flocculent, it actually means woolly or like fuzzy. So this is where you can't clearly see the two arms. So here it's really more of a mess. There aren't two clear defined arms. The Milky Way is somewhere in between. So if you remember, the Milky Way has a couple of spurs and detachments, but it's not quite as woolly or messy or fuzzy as this galaxy is here. So one thing to think about when we're thinking of these spiral bands is that star formation can be self-sustaining. So remember that the formation of a star could cause shock waves that then trigger star formation nearby. So we can have that self-sustaining circle where a star formation in one place sparks star formation in another place, which sparks star formation in another place relatively close by. But we have differential rotation that's going to drag the inner edge of a cloud ahead of the outer edge of a cloud. So the inner part closer to the center of the galaxy is going to be dragged ahead because it's going to be moving faster, whereas the outer part, more towards the outside of the galaxy, is going to lag behind. So that sort of makes the spiral arm shape. So that can cause spiral arms of star-forming regions. So maybe the spiral arms are kept up or self-sustaining in terms of constantly forming stars, which sparks more star formation that is kept in this spiral arm shape. So the most up-to-date or the most widely used current theory is that the spiral density wave theory creates the two-arm spiral patterns. So that two-arm here, this grand design pattern, is caused by that spiral density theory. But also, the self-sustaining formation of stars is what produces the branches and the spurs. So like in our galaxy, we don't have a perfect two-arm spiral pattern because we have this self-sustaining star formation occurring that's causing the branches and the spurs outside of these two spiral arms. So in addition to the spiral arms, we do actually have a center of our galaxy. So remember, the center of our galaxy is pointed towards Sagittarius. Well, from our viewpoint, it's pointed towards Sagittarius. And it's not at all visible in the visible wavelengths. So the center of our galaxy, which we call the galactic nucleus, the same way the center of an atom is a nucleus, we call this the galactic nucleus. It's completely hidden by gas and dust in the visible, but it can be observed in infrared, in radio, and X-ray wavelengths. So we have observed it in other wavelengths. So the very center is shown here as a very, very bright white area. And then this orange on the outside, that's all supernova remnants. So saying large stars have formed nearby because we know that there are supernova remnants around the galactic nucleus. So when we think about our galaxy in terms of what is it actually made of, we think about metals versus non-metals in our galaxy. So for astronomy, we consider a metal to be any element with an atomic number higher than that of helium. So anything larger, with more mass than helium, we consider to be a metal. So if we look at a graph of relative abundance and atomic mass, we see helium very, very close to hydrogen. We see most of the elements in our galaxy is hydrogen. We knew that already. Almost everything is hydrogen. But everything after, or, on this graph after, but what we really mean is anything with a higher atomic mass than helium is considered to be a metal. So all of these elements here that make up still a good amount of our galaxy, those are metals. So this scale is a little hard to look at. If we look at just a linear scale that goes from 0 to 10 to the 12, we can see how much hydrogen is in our galaxy compared to how much helium, compared to how much of everything else. So there's a measurable amount of metals in our galaxy, but it looks like almost nothing compared to how much hydrogen is in our galaxy. So hydrogen really is the most abundant by far, second to helium, and then everything else, which we consider a metal, is significantly less than the amount of hydrogen that we have. So thinking about metals is important because we use the chemical composition to break up our stars into populations. So stellar populations, we consider there's sort of two groups of stars, or two families of stars in our galaxy. So there's population 1 stars and there's population 2 stars. Population 1 stars are generally very young stars that are metal rich, meaning there's a lot of metal within the star. A lot of metal being 2 to 3%. So it's only 2 to 3%, but that's a lot compared to population 2 stars. These population 1 metal-rich stars are pretty much always in the disk component of our galaxy, so they are relatively young. They're still within that disk. Population 2 stars are metal-poor stars, meaning they have less than 0.1% metals, and they're generally very old. So these stars are found in the spherical component of the galaxy, so in that halo area, but they were formed when the galaxy was very young. So when the galaxy was young, before there was a lot of metal available, these population 2 stars formed, and they are all in the halo portion, not in the disk portion of our galaxy. So they have the randomly tipped orbits. They don't have the orbits along the track of the disk. They have those tipped orbits that range from circular to elliptical. So this figure here, it's a little hard to see, but you can see in our population 1, these spectral lines here showing the different metals are a bit darker than the bottom here for population 2. You can see more clearly the lines from the metals in the population 1 stars than in the bottom, the population 2. The two different types of stars, why are these populations important? They give a lot of clues about the history of our galaxy. So we're getting into a little bit of how did our galaxy form, which we still don't really know, but we have some guesses. So those population 2 stars, the older stars, they're survivors since the very beginning of our galaxy. So sort of the earliest generations of stars, that's why they're the oldest, they were formed when there wasn't much metal in our galaxy. So there wasn't much metal to form these stars. So these are sort of survivors of the very, very beginning of our galaxy. So they're very long-lived, they're super old, they're low mass because there isn't much metal. Population 1 stars, however, formed more recently after there was metal, after the ISM, after the galaxy was enriched with metals. So the stars forming now have a higher percentage of metal than older stars. So the population 1 that's formed in the very beginning, there was no metal to be had, so the stars don't contain any metal. Whereas stars forming now, let's say, are going to have the highest metal percentage because metal has been slowly accumulating in the ISM and in our galaxy. So our galaxy is about 13 billion years old. How do we know this? Since we're able to guess or determine relatively confidently the age of star clusters, we can actually estimate the age of the galaxy by looking at the age of the oldest stars in the galaxy. So it sort of gives us a limit on the age of the entire galaxy, but it's not very certain. It could be older. So we know the distance to these star clusters, that allows us to determine the age. So the average age of our oldest star clusters are about 11 billion years old. The age of our halo, so the halo portion of our galaxy, we've determined there's stars that are about 13 billion years old. So we know that our galaxy must be at least 13 billion years old for it to have stars that are 13 billion years old within it. So for the last part of this lecture, we're going to talk about how the galaxy formed. I just have a couple more slides. We're going to go over two different hypotheses for the formation of the galaxies. So there's the top-down hypothesis, and then there's the bottom-up hypothesis. So we'll go over the differences and then some of the drawbacks or the things that aren't quite explained. So first, the top-down hypothesis is the idea that the galaxy formed from a single very large cloud of gas. And that cloud of gas, these figures on the side are from the textbook, that cloud of gas contracted, got smaller to form our galaxy. So during the contraction, it didn't contract evenly. The cloud actually fragmented. So there were these different, if you see these tiny dots all around, tiny little bits of cloud which got left behind as the galaxy's collapsing. So here we have the galaxy, about to be the galaxy collapsing. And here we have these stars and star clusters that are left behind. So the star and star cluster left behind is what created the halo area, what created the spherical component of our galaxy. The disk portion, however, formed as the clouds in this spherical piece continued colliding and mixing. So it continued colliding as it's spinning. It ended up flattening out, sort of like pizza dough. So if you had a ball of pizza dough and you spun it around on your finger, it would flatten out into a disc, into the shape of a pizza. So that is what they think might have happened to our galaxy, is that the disk portion was formed as the ball of pizza dough, or this giant ball, this giant cloud of gas actually contracted, formed into this flat disc, spinning disc, I should say, spinning in a rather uniform way. So this process would take billions of years, so this is not as quick as, say, making a pizza. But the abundance of metals would gradually increase with time. So there would be metal increasing with time, and stars would be born as this disk was flattening. So as we're contracting, as things are combining, colliding, mixing, we would have star formation in that flattening cloud of gas. So that's the top-down hypothesis. There are some issues with it. The main ones being that not all star clusters have the same age. So in this hypothesis, you would expect that the halo is what formed first. So in the condensing, as this cloud is condensing, the pieces of the halo are left behind. However, in reality, we find that there are some young star clusters in our outer halo. So that is not explained by this hypothesis. So how could there be younger star clusters out here when the only star formation is occurring in the disk? That is not explained by this hypothesis. This hypothesis states that really the distant star clusters in the furthest pieces of the halo would be the oldest. Excuse me. It also states that the oldest stars would be metal-free. So there was no metal, so the oldest stars would have no metal. However, our oldest stars are metal-poor. They're not completely metal-free. So this means there must have been some metal in existence before the formation of our oldest stars in that halo. Metal comes from the formation of large stars. So as our large stars create things like iron, which is a metal within their core before they explode. If you remember back to star formation, this top-down hypothesis is saying that there was no metal present when this halo was created. However, we know that there must have been, so that is another thing that's not explained well by this hypothesis. There must have been massive stars in existence to create the metal that we know is there. So two main problems that we're going to talk about with this top-down hypothesis. So last thing for today is the other hypothesis, which is considered the bottom-up hypothesis. So this is saying that the galaxy began as a large cloud of gas, again, where there was almost no metal, and the first stars that formed were metal-free and very, very large. And that first generation of stars, they formed quickly, they evolved very fast, and they exploded into supernova, which allowed for enrichment of metals into the cloud of gas. So as these very large stars evolved and aged, they're going to be producing metal in their cores. If you remember how very large stars age, they're going to produce metal in their core. When they explode, we will then have that metal available in this cloud of gas. So this first generation of stars, they don't survive, but our population 2 stars are made up of the metal that they produced. So then the bottom-up hypothesis says the central bulge and the halo of our galaxy actually formed from collisions. So material that was on the outside of our galaxy that ends up actually being drawn in by gravity and absorbed into our galaxy. So the bulge and the halo are created from outside material that gets absorbed and mixed into our galaxy. So this is maybe a little more plausible, especially since recent evidence actually shows that the Milky Way did form through the merging of smaller galaxy clouds. So we have evidence that actually shows that these outer galaxies were brought in and absorbed into our galaxy. So this bottom-up hypothesis is the one that seems the most plausible right now. Again, they're both still hypotheses, so we don't have enough data to prove at this time true or false of either of them. But this hypothesis much better explains the ages of stars and star clusters on the outer edge of our galaxy. So pulling in material from the outside means you're pulling in material that doesn't have anything to do in terms of age with the rest of the galaxy, so you can have that sort of mismatch in ages as you move outwards from the center of the galaxy, which the top-down hypothesis didn't have. That was one of the main issues. So that is, those are the two hypotheses for galaxy formation. And that is all that I have for you today for this week. I would do your second lecture assignment now. It's all about the different pieces and components of the galaxies. So please remember to use the discussion board if you have questions for each other, for me. You can also shoot me an email or attend office hours. Also, great job on the exams. The average grade was pretty high, so I was happy to see that. Also happy to see that the online exam worked at all. I was pretty nervous when you guys were supposed to be taking it, hoping that everything would go okay, and it seems like it did. So I hope you all have a great rest of your weekend, or hope you all have a great week, depending on when you answer this, and have fun with the work for this week.